Okay, thank you for coming to 131st NIA CFD Seminar. And today we have speaker Rubel Das, originally from Bangladesh. He got bachelor's and master's from University of Technology, Engineering and Technology in Bangladesh. And then he went to University of New Mexico and he got PhD there. And that's where I think he worked on the CFD work. Today he's going to talk. Currently he's here at NIA. He's a postdoc at NIA, working with the NASA people, Stage 3 ISS team. Today he's going to talk about wind farm optimization and analysis of complex wake structures. So please take.
Hello, good morning. Thank you for being here. My name is Rubel. So I'm originally from Bangladesh, like you mentioned. So I did my bachelor and master's back in Bangladesh University of Engineering and Technology, and then I came here. I did my PhD in University of New Mexico. So during my PhD, I basically developed a solver. That solver has DNS and LAS features, but I just used the LAS part of the solver to analyze wind farm optimization and complex wake structure. So today I'm gonna talk about this. I hope you guys will enjoy a little bit. Thank you.
So these are questions.
Yeah, if you have any questions, you can stop and ask me. So these are the outlines: introduction, numerical methods, validations, and two case studies. First case study is exploring the role of down proximity in the wind turbine wake behavior, and the second case study of effects of yaw angles and wind speed on wind farm performance. And finally, I'm gonna talk about some future works and conclusions. So IPCC reports that wind energy has to increase from 20% in 2018 to 67% by 2050 to limit the global temperature rise 1.5 degrees Celsius. Wind energy has been a forefront for this movement, especially to reduce carbon emission. And also, wind energy has importance to lower the wind energy cost, also creating new jobs and ensuring more diverse and resilient winds. On the right, you can see the complex wake structure of wind farm, and this is from our simulation. This is two figure picture. One is offshore in Denmark, another is onshore, developed by GE. So the motivation of this work was actually to develop a numerical framework to analyze wind farm cases or wind turbine cases as much possible to imitate the real world characteristics. And for that, I developed a solver, CFD solver that has DNS, also LAS. And but I'm gonna use the LAS part of that solver to study some wind farm cases, and this is gonna eventually gives us some better understanding of the underlying physics of the wake interactions. That's gonna lead to more efficient wind farm control strategy. So for this current implementation, we considered a neutral atmospheric boundary layer, neglecting the Coriolis force. The continuity equations and the momentum equations, Einstein notations. UI is the field chart of the resolved velocity for the LAS work, and X is the Cartesian coordinates in the ith directions. P star is the modified pressure, and C is the smoothing coefficients that's needed for the LAS calculations, and S, I, J is the resolved strain rate, and modulus of that is the strain rate magnitude, and F, I is the body force to imitate the turbine thrust force. And since it's LAS, so we need to parameterize the AGS terms, and that has been done with Lagrange's average scale pivoted model. This is the by far the best model to imitate, to calculate the smoothing coefficient, because it's actually calculate the coefficient at every grid point, and it offers a better representation of the turbulence structure and their interaction with resolved flow structures.
Do you account for gravity?
No. So these are the solver numerics. As I already mentioned, that the solver has both direct numerical simulation, also largely simulations. And the second feature of the solver is called concurrent precursor method, which saves times and storage to run simulation. This was one of the initial motivation to develop this solver. So what happens is that we concurrently run two solver, two domain. This is the recycler domain or the precursor domain. This is the test domain. So what happens is that if we run just one domain and if you use the periodic boundary conditions, so this wake effect's gonna come back in the inflow. So to avoid that, people used to at first just run one simulation and solve saves the inflow data and then rerun this test domain, reading this inflow data, which takes a lot of spaces and times to run one specific case. So to avoid that, we kind of implemented this concurrent precursor method. And we use structured, staggered, and finite volume formulation with second order central difference scheme. And the second order Adam Bashford was applied on the convective and the stress term. And fractional step method was used to uncouple the pressure and the flow field from the momentum and continuity equations, and which derived a Poisson equation. We solved that Poisson equation with the multi-grid solver, open source solver called High-fidelity. And to parallelize that solver, we used MPI. And we tested both convective form of the convective terms. And we found that actually divergence form of the convective terms was better, slightly better than the advective term, advective form. And we used explicit box and top filtering for the alias filtering procedures.
What's the difference between convective terms and advective form?
So the divergence form of the convective terms.
What is the advective form?
Advective form is so there are like two forms of the convective terms. One is advective, one is divergence. Divergence is actually putting the velocity multiplication inside the gradient, and advective is putting one of the velocity field outside the gradient.
Conservative and non-conservative form. And,
yeah.
Okay.
Yeah, since it's actually we actually solve the continuity equations every time step, so it actually justifies itself for every time step.
So this is explicit. So like
yeah. So for the alias we use explicit, but DNS actually has implicit implementation. And
even when you have fractional step method, so that how you still use fractional step for DNS?
Yeah.
So you implicitly basically couple several steps.
Right. Yeah. And that implementation took a long time actually to parallelize that actually. And there is this solver has another feature, it's called shifted periodic boundary conditions, which actually reduce the runtime of the turbulence simulation. Because if you run a turbulence simulation, it takes a lot of time to get a statistically uniform flow, but still you will have some large streak structure. So to get a uniform structure, you can use this boundary condition, but this boundary condition has some limitations also.
And when you say structure, you essentially mean Cartesian, right? So that the grid or its body field. So
it's Cartesian. Like you're talking
so
about
like for geometry representation, you use some cut cell method, so that how you represent geometry. This is Cartesian grid, so that like blade intersect Cartesian grid, so that you use some cut cells or approach. Or...
Yeah, so it's so staggered. It's not actually marker. It's kind of like a marker and cell, but yeah. So it's a staggered Cartesian grid. I'm not sure what's.
Yeah, you staggered, right? So that basically different equations defined in different places. Right.
right? So
Right.
basically
Yeah.
on the Cartesian grid, some equation defined in the middle of the cell, some at the nodes, some maybe at the edges.
All right. So
So we do linear interpolations to get those into the specific.
But when blade is curved, right, your grid is kind of curved with geometry, or it is still purely.
Still actually Cartesian. Oh, you're talking about the wind farm turbine implementation. Yeah. So it's still actually. So there is several implementation how you can actually imitate the turbines. One is called actuator disc. It basically imitate the force, thrust force, but it's force on the Cartesian grid. We do not actually imitate the actual turbine structure. Actually, the grid.
Okay.
Yeah.
You do not model
No.
details of the
Yeah.
wind turbine. Okay.
Right. Yeah. So these are the boundary conditions. So for the first domain, the precursor or the recursive domain, we used periodic boundary condition in the horizontal directions, and inflow and outflow boundary condition with zero gradient in the streamwise direction, and periodic in the spanwise direction for the test domain. And this is a new boundary condition. We tested several boundary conditions. We found that this boundary condition was better to calculate the imaginary points that's going to needed for the convective drums. And stress-free boundary condition was used at the top. Since it's LES and doesn't resolve the viscous layer, we used the law of the wall based on the similarity law. And since we need to apply this wall stress at both directions, so we kind of split that in this manner. So we used a time adaptive wind turbine model. It's called actuator disc modeling. And so this is the thrust force. This thrust force has two distribution. One is elliptical distribution. Basically, it distributes the total thrust force in the turbine plane using elliptical formula. And since this thrust force is huge, and if you apply this on just only one cell, it's going to be unstable. So we used another function, it's called Gaussian function, and we smooth it over the streamwise direction. Still, there are some instability arises because of the instantaneousness of the flow. So we kind of use the time averaged or time adapted formulations to relax this value using these formulations. And this T is the time window. And here is the induction factor, CET is the thrust force. Since we're gonna study wind farm cases with EOing, EOing is just when you rotate the turbine in the particle directions, and it actually helps to shift or redirect the wake so that we can actually get better power output from the wind turbine. So we implemented the EO implementation in the solver. So basically, it takes the thrust component perpendicular to the rotor plane. Since this component is actually not aligned with the Cartesian grid, we have to split it into two Cartesian component. One is the fx and there's z, and we're going to apply this to the respective momentum equations. So now I'm going to talk about the validations. So on the left-hand side, you can see the input profiles from the precursor simulations. And you can see that actually for different velocity, it actually matches with the theoretical theoretical profile of the log law. And especially it matches quite well in the region of interest where the turbine are placed. And on the right-hand side, you can see the log profile with the log scale. And you can see that actually domain 1 is the precursor domain, and domain 0 is the precursor domain, and domain 1 is the test domain. And they should be matched exactly, and there are two actually. So this is a good sign of the solver's accuracy.
What is it? LOTW? What is this called? Like LOTW or
Log of the wall.
log of the wall. Yeah.
So this is the theoretical profile with the black line. So these are some other validations. So this is the energy spectrum. So energy spectrum has two distinct slope, -1 and -5/3. As you can see that this energy spectrum follows the theoretical slope quite well. And this is another validations. Basically, the total stress of the subgrid shear stress and the Reynolds shear stress. If you add these two, and you get the theoretical match, which actually start from 0 at the top and comes at 1 at the wall. And obviously, those stresses are actually normalized by the square of the friction velocity. And this is another validations. Very common for the large eddy simulations, and it's called mean velocity gradient profile. This is the theoretical line, and as long as it stays in between 0.8 to 1.44, it matches quite well. So since we have
this is a flat plate computation, right? So that you basically
it's basically a flat plate. Yeah, it's a more like a half channel.
Okay.
Yeah. Yeah. So this is the wind farm validation. So for this wind farm validation, we consider the 3x10 wind farm simulations, and we used actually this method as described earlier, and we validated the experimental results conducted by Shamaru and Portugal. So these are the dimensions we used. One thing to notice here is that we use the same thrust coefficient obtained from the measurement.
So you have actuator disk to represent each individual turbine, right?
Right.
So you source method for approximating this actuator disk, so that basically you apply sources to points that to places that are basically crossed by this actuator disk, and you have some distribution of thrust and torque.
Exactly. Okay. Yeah. So these are the input profiles compared against the wind tunnel test measurements. As you can see, this is the velocity profile, and this is the turbine intensity profile. They match quite well, especially in the region of interest where the turbines are based. And there are some discrepancies, and these are very common when you compare the LS simulation with experimental results. This is instrumental stream-wise velocity component. As you can see from this figure, the interaction of the weight structure behind the wind turbines. This has another profile. You can see how actually wind turbines are affecting the upstream wind turbines are affecting the downstream wind turbines. These are the time average velocity deficit. You can see it more clearly how it's actually affecting the downstream turbines. And you also can see that actually these turbines also generate or produce a boundary layer. As you can see, this actually shows like a boundary layer growth. It's called a wind farm boundary layer. And this is the velocity deficit profile for the first 5 rows against the experimental results. As you can see, they match quite well, especially in the region of interest. And there are some mismatch because we didn't actually model the turbine tower and the nacelle. So we just modeled the turbines only. So turbines actually has the nacelles, also the tower. So we didn't model that actually. This is the last 5 rows of the velocity deficit profiles, and these are the turbulent intensity for the first 5 rows. As you can see that turbulent intensity, they kind of has little bit more discrepancies in the near wake than the far wake. So what happens is the near wake, it actually has the tower and the nacelles, which generate more turbulence in the near wake, means like 2D or 1D and 2D. But in the 3D and 4D downstream, it's kind of dissipate the turbulence. So that it has a better matching with the experimental results. This is the last 5 rows, kind of shows similar results. Since we implemented the EU implementation, so we did the validation for this implementation too. And since we don't have experimental result for utility scale means actually how turbines are, the actual turbine size. And so we compared it with another simulation results. As you can see, they actually match quite well, but there are some discrepancies because we kind of used low resolutions. And this is the contour plot which shows the deflection of the wake due to the U implementation.
You probably mentioned it somewhere. Maybe how long are your computations? Over what interval you average to get all this results?
So there is like a I think 70, I think, flow through time. You have to actually at least average 70
flow through means through entire farm.
Right. So
right.
Yeah. So at least 70, but you can actually still see some large sticks, but here you don't see them, but you see them mostly if you have a smaller grid. Then these large streaks actually they don't go away. That's why you need that shifted periodic boundary conditions actually.
But do you kind of evaluate how good is your averaging? So do you try to average over different intervals and compare if your average values kind of stabilized?
So we didn't do like this kind of like quantitative analysis, but what is happening that so this is just mean velocity profile. Mean velocity profile, if you just take a couple of flow times, it's kind of gives a statistical uniform profile. But for the higher order statistics like turbulence intensity or some skewness or something, you need more time average data. Yeah. But as long as you have like around 70 flow through time, so it gives a statistical homogeneous flow. So this is the unitary scales, means we compared this implementation derivation against wind farm studies, experimental results, and also with two other simulation results. As you can see, they match quite well with experimental, also the other simulations. And there are some which match with the turbine intensity, but this is very common. As you can see, that the other simulation studies also have this mismatch. And so this is very common in wind energy simulations. So this is the first case study exploring the role of the ground proximity in the turbine wake behavior. So the motivation was actually, so the impact of the gap was underexplored, especially with the proper LES framework. And the previous studies mainly used reduced order or analytical model. And there were some LES studies, they basically tried to evaluate those reduced order model. So the primary objective of this study was actually get a better understanding of the influence of the gap and overall dynamics and characteristic of the wave. This result was presented in APS meeting. So these are the dimensions and the parameters we used for this study. Two things to remember for the result analysis, that we considered two cases. One case is with half height 90 meter and another case with half height 103.5 meter. But for both cases, the rotor diameter was same, 126 meter. So following the NREL 5 megawatt turbine. And so we defined this case as 0.25D and second case as 0.35D. As you can see that this is just the simulation runs without any turbine. This is the test domain. We have just only one turbine. Yeah. So this is the contour of the streamwise velocity component in the XY plane. As you can see, this is the smaller gap. They actually have more interaction with the ground and less higher moment of flux through for the lower gap. And but for the larger gap, you can see that higher momentum is flowing through the gap. And this, since this turbine is actually placed at a higher altitude, it actually brings more turbulent kinetic energy being to the turbine half height. So this is the average profiles. As you can see, these average profiles also show the higher moment of flux flowing through the larger gap. And also you can see that actually for the lower gap, the wake kind of persists longer than the larger gap, which means that wake is recovering faster for the larger gap. you can see the same features in the lateral profile, lateral contour profile. As you can see, two features here, that actually the width, also the length of the wake actually changes. And for the larger gap, it's actually smaller, the length, also the width. And we suggest that the wake is recovering faster for the larger gap. And this is a mean velocity contour. It shows the same features as the instantaneous profile. These are just another two instantaneous profiles cut through the rotor plane. As you can see, that more interactions of the turbulence structures underneath the larger gap. This is contours of the same contour plot, but a mean averaged. And you can see that actually higher gap actually has more high velocity. So this is the vertical wave profile comparison. As you can see from this, that fluid gets accelerated more for the larger gap. And also you can see from here that actually the wind shear is stronger for the larger gap, which actually brings more turbulent mixing in the rotor area. From this lateral wake comparison, you can see that actually the shape of this wake profile, as you can see, the shape is actually gets smaller for the larger gap. We suggest the wake is recovering faster for the larger gap compared to the smaller gap. So this is the vertical turbulent intensity profile comparison. So for the larger gap, you can see that actually turbulent intensity is higher. We suggest that the turbulence is actually generating more in the downstream, which is like accelerating the wake recovery. This is the lateral turbulent intensity profile. On this also, you can see that actually the turbulent intensity is higher for the larger gap. Suggests the same conclusions as that wake is recovering faster for the larger gap. And these are the conclusions for this case study, that gap between the rotor disc and the ground affects the recovery of the wake in the turbine, and larger gap helps the faster recovery of the velocity deficit compared to the smaller gap. This is the second case study, effects of yaw angles and wind speed on wind farm performance.
So actuator disc always assumed to be kind of orthogonal to the ground, so that when you say like 0.35 d, you mean so there is a disc and this is this distance.
Yeah.
And like the disc is always like this, it's not like this or.
Yeah, so this is the case study. We're gonna study that rotation of the turbine actually. So the rotation of turbine, there are two different mechanisms. One is called yaw-ing. If you rotate the turbine in the vertical direction, it's called yaw-ing. And if you rotate the turbine in the horizontal direction, it's called tilting the turbine. So the most common is actually yaw-ing.
Yeah, it does not change.
It does not change actually, but if you tilt it, it will change.
But you measure still like the gap measured from kind of lowest point to the ground, so that if you tilt, so that it's basically increases the distance from.
Right. Yeah. So wake steering is called like tilting or yawing the turbines, which basically become very important if you place the turbines very closely, because if you place the turbines far from one each other, from one each other, then it's gonna be very costly. And so wake structure within the full wake and the partial wake conditions under different wind speed and yaw angles are underexplored. And full wake means you are not actually like rotating the turbines. It's gonna have the same shadow effect for the subsequent downstream turbines. And partial wakes means you are kind of rotating the turbines. And most studies actually they did based on the layout changes. Layout means not all the turbines will be in the same row of the column, and or some reduced order modeling. So no rigorous study actually conducted to see this combined effect of the yaw angles and the wind speed on the wind farm performance and wake physics. And this result was presented in the Energy Journal. So these are the dimensions and the parameters. One thing to notice here that actually usually, so for all the cases, we use the same turbulent intensity and we use the same turbulent thrust coefficient. Usually what happens is that in the real world, actually, they increase the thrust coefficient for the downstream turbines since the downstream turbine gets a low velocity. And these are the 9 cases. So the first 3 cases have the same velocity, but different yaw angles, 30 degree, 20 degree, and 0 degree. D, E, F have the same velocity. The highest velocity we consider 10.4 meter per second, and this is has the same orientation 30 degree, 20 degree, and 0 degree. And G, H, I has the lowest velocity 4.3 with the same yaw angle combinations 30, 20, and 0. And this is the recycling domain. That's how the 3 rows of turbines are placed. And this is kind of the convention. The minimum distance we have to keep between the turbines is 5 diameter. So this is the time averaged velocity deficit profile in XY plane. As you can see that wake steering affects the deflection of the wakes. As you can see, there is no yawing. This is 20 degree, this is 30 degree. As you can see, that if you increase the yaw angle, the wake deflects it more and more. And you also can see that for the first row of turbines, the wake deflects less than the third row, and subsequently for the downstream turbine, the wake is actually deflecting more and more because of the secondary effect of the wake steering. And another thing to notice that if you see downstream, actually the wake actually widens because of the mixing, and eventually they actually gonna mixes with the they mix with the mean flow if you plot it until the last plane. So this is the turbulent intensity distributions. As you can see, this turbulent intensity has the higher turbulent intensity at the edges, and where there is like a higher turbulent, higher wind shear, and it has this dual peak distribution, especially if you see for the non-yawed case where there is no yawing of angle. And this distribution of the turbulent intensity axisymmetric for the non-yawed case and asymmetric for the yawed case, and this asymmetry increases with the increasing yaw angles, and which eventually leads to asymmetric wake recovery with increasing yaw angles. So this is the velocity deficit in the YZ plane. As you can see that actually yawed case create counter-rotating vortices at the top and the bottom of the wakes, which kind of shifts the wake from the row or the wake line. And these yaw angles, as you can see, this is 0 degree yaw angle. As you can see that if you increase the yaw angle, this counter-rotating vortices shape and the structure changes, eventually affecting the whole flow dynamics. And on this figure, you probably won't see the effects of the wind speed. So the first we see basically the same wind speed, and this DEF is the highest velocity and DHI is the lowest velocity. But this velocity influence on this wake structure is not easily understood from this contour plot, but we'll see this in the velocity plots. This is the turbulent intensity profile in XYZ plane. You have the same distributions as we see from the velocity, and that also has at the top of the boundary, sorry, at the top of the edge of the turbine, the higher turbulence intensity as suggested by the higher turbulent kinetic energy mixing at the top edge of the turbine. And as you go down, you can't actually see the difference, the influence of the wind speed on this structure, but usually at the lower wind speed, there is low turbulent intensity generations. So the velocity deficit field in XY plane. So as you can see that actually the yawing of the turbine affects the particle distribution or the wind shear of the velocity field. Same feature we can see from the turbulent intensity XY plane. As you can see that more turbulent intensity for the non-yield case because it has more mixing and it's not shift. It has less mixing and it has so it's more turbulence there and it has more mixing. So that if you yaw the turbine, so it actually kind of try to dissipate the turbine intensity. So these are the lateral velocity deficit profile, and as you can see that these turbines so this is X by D means 2 downstream and X by D equal to 4 means 4 downstream from the turbine. As you can see that actually if you go downstream, the width of the lateral velocity profiles widens and also the magnitude also changes, reduces because of the turbine mixing. And as you can see actually for the yacht case, this is kind of 2-dimensional Gaussian axisymmetric distribution, but for the not for the non-yacht yacht, this is non-yacht case, and for the yacht case, it's actually become non-axisymmetric, and non-axisymmetry increases with the increase of the yaw angle. And one thing actually to notice here is that so this is the red line is the first row and the black line is the second row and the third green line is the third. As you can see that actually in the third row, as you go downstream, the waves gets more axisymmetric because of the secondary influence of the wave behavior. So this is the lateral turbine intensity profiles. As you can see here that this turbulent magnitude and also the distribution changes as you go downstream because of the turbulent mixing. And also we can see that actually this has this kind of the same features that velocity deficit profile. As you can see from here, this maximum locations, also the distribution of the turbulent intensity changes as you go downstream. So this is one of the important profile comparison of the lateral velocity deficit profile for different velocity and yaw angles. So one thing to notice here that for the non-yaw case, this column and this column, we don't see any influence of the wind speed actually. But for the 20-degree yaw angle, if you notice that actually for here, so the green line is the lowest velocity, and the red and the black line is the highest velocity. For the lowest velocity, you can see that actually they actually don't shift much from the center line compared to the highest velocity, which means that actually they are affecting more the downstream turbines, which actually eventually affecting the wake recovery. So if you shift the wake more from the turbine actually, then you have more wake effects in the downstreams. And here, the distribution of these velocity profiles for different velocity, different rows, but not much influence of the wind speed on these distributions. This is the comparison of the lateral turbulent intensity profiles for different velocity and yaw angles. The same features we can see here, especially for the 20-degree yaw angle. As you can see that the higher velocity actually there shifts the turbulent magnitude, also the distribution air from the central line. Central line is the zero line actually here. And for the lowest velocity, it doesn't shift that much. That suggests that wake is actually affecting more for the lowest velocity in the downstream. This the comparison of the particle velocity deficit profiles here you can see that the Ewing has a lot of influence on the particle profiles as expected, but for the 20-degree Ewing gels, you see here that wind shear is kind of weak for the lowest velocity, but for the highest velocity, wind shear is stronger, which kind of brings down more turbulent energy in the rotor plane. This is the turbulent kinetic turbulent intensity profiles. It has the same feature as turbulent, same feature as the velocity deficit profiles. As you can see that at the higher edge of the turbines, there is more turbulent intensity, which suggests more mixing at the top edge of the turbine. And from here also you can see that actually lowest velocity has less turbulence intensity, which suggests that wave is not recovering as fast as possible. So this is the main conclusion. Basically, this is the main parameter, the relative power output. As you can see that from this figures, that this is the green is the for the non-yacht case, and this is for the yacht case. As you can see that if you rotate the turbine or increase the Ewing gels, the relative power increases. But one thing from here to notice is that the second row produces less power than the third row, because the first row actually feels a lot of velocity deficit and low turbulence levels. So the wave doesn't recover as fast as possible for the second row of turbines. But as we go downstream, it has more time and more mixing, and the wave recover faster for the third row and concurrently for the other downstream row. And another thing to notice from here is that this for 20-degree Ewing angle. So for the lowest velocity, as you can see that the lowest velocity for 20-degree angle produces less power for all the row of turbine, which suggests that actually lowest wind speed affects the downstream turbine way severely than the highest wind speed. So the black line is the highest wind speed, 10.4. So there is like 1 or 2%, but this 1 or 2%, if you actually accumulate those differences of these effects, and this gonna save like millions of dollars for like one wind from over the year. So if there is like a 1% or like less than 1% increase of this relative power, that makes a huge difference for the overall power generations. So these are the conclusions. So we saw that wind speed variations has little influence in the wave structures at any Ewing angle, except for the lowest wind speed, 4.3 at Ewing angle of 20-degree. And at lower wind speed, turbulent intensity profiles show reduced deflections, particularly at 20-degree Ewing angle. And power losses also follows the same characteristic as the turbulent intensity and velocity profile. So power losses are more for the lowest velocity, especially for 20-degree angle. So these are the final conclusions. So for this work, we developed this solver, which has DNS and LES features. And we did some validations, and we studied the effect of ground clearance. And we saw that higher ground clearance has faster wave recovery. And we tested another case study. And we found that wave losses are higher for the lower wind speed, especially 20-degree angles. So those are the future works we tried to do. So we just included 3 rows of turbine. Probably we can actually extend it for more rows of turbine, or we can consider the extreme wind speed conditions, but because we just considered highest velocity 10.4. So, but we can simulate for higher wind speed. And we can also study this with other wind turbine implementations. It's called extruder line method, or rotating or including the turbine tower or nacelle. And we also can study with the atmospheric stability, meaning actually including the temperature influence in the solver. And once there will be better understanding of the rotor gap, we can actually extend it for several rows of turbines. Thank you.
I asked a lot of questions, but
No, it's good. Yeah.
So one about physics. What's special about this speed and angle? So it's like there is some resonance for this. Why like particular wind speed and your angle much different from others? There is understanding for this, or?
So why I chose those specific?
No. You basically, I think from conclusion you say that there is a big influence of speed 4.3 meter per second and 20 degrees Leo, and for other angles and ranges of speed, wind speed, there is no much influence on weight. So what is special about this particular combination? 4.3 meter per second and 20 degrees, why it has influence on other combinations or not?
Right. So what happens is that so there is like a theoretical calculations where we found out that 20.7 degrees yaw angle is the highest you can increase for any yaw angle. If you increase it above that, actually, then it doesn't actually help the relative power output. But so 20 degrees is kind of lower than 27 degree. And what happens is that for the lower wind speed, the wake doesn't actually deflect that much. So, but if you rotate the turbine, if it's at the highest wind speed, then it's actually deflects more wake. And if it deflects more, it's not actually affecting the downstream turbines. But for the lower velocity, it's not deflecting more wake. So it has this for a couple of reasons. One of the reasons is that turbulent intensity also is not generating as much as the higher velocities. So eventually, the velocity is not actually velocity deficit is not shifting air from the turbine row, and also the turbulent generation for the lowest velocity also less, and that's why that wake recovery.
But if you would increase, for example, your angle beyond 20 degrees, you still expect to see, and say, let's say keep the same wind speed, you increase, you still expect to see strong effect on the wake, right? So that
right.
So it's basically 20 degrees is some like initial angle, so that if you have more than this, you have strong effect on the wake. If you have less than this, you don't know. Then with speeds also, so that if you like increase, like let's suppose you have 15 degrees. I don't remember exactly what you did, and you increase speed, wind speed, so that then you will have more effect on the wake of speed. Okay, basically, is this expected result, so that you knew in advance that this 4.3 meter per second and particularly your angle should be different from other results that from other conditions that you studied? Is it kind of expected, or this is new finding from your study?
So it's kind of it's not like unexpected. Obviously, if you think about it like intuitively, it makes sense. But the thing is, our idea was actually give like underlying physics information, like what actually happened, why we are getting lower output for the lower velocity. So what is actually happening is like physics wise actually. So we try to understand the physics actually. So you can so we know that there is less turbulence for the lowest wind speed. So there are some mechanisms you can actually artificially or like some other mechanism you can increase the turbulence. So like for example, there are some studies that actually they put some kind of structure in between the turbines row, so which actually generate more turbulence and eventually helps to recover the wind wake actually faster. So we know that actually we need to increase the turbulent intensity, but how much we gonna need to increase it, or for what wind speed we need to increase it for. So yeah. So it's
probably ask naive question because I'm not.
No, that's fine. Yeah, absolutely.
I have some numerics question, but maybe it's first need to ask online.
Any question online? No.
Okay, so how big actually your computations? I mean, how many degrees of freedom you have in your discretization? How many actual time steps you do, and how do you run this? How much time it takes?
Yeah, so code developing this code was a lot of struggle actually. So so the UNAM is kind of like a mid-range university, so we don't have a huge computational resource. And initially my professor just kept asking me, add this feature. So it's not only alias, DNS, and there are, so I was the sole developer of this solver, and I had to learn everything, coding. I started to learn coding and everything. But to answer your question, basically for these alias simulations, we ran one case actually we take, I think, like 1 month actually at least, just to run just one case. And time step was, so for this wind speed variations and UM variations, we ran one case 275 flow through time to get the statistics. So it was more than enough. Usually you need 70 flow through times, but we did more than that because turbulent intensity profiles we are getting, it still doesn't have a statistically homogeneous profiles. So this was one of the reasons we actually ran those more than enough.
Okay. And you mentioned you have some multi-grid inside. That's for implicit computations, I guess, right? So that, you said that you use some multi-grid package inside.
Yeah.
That's probably for implicit computation, right? So
yeah, for the not implicit, it just solve the position equation, pressure position equations. Yeah.
For implicit, right? So that's what I see.
Yeah.
Yeah. Okay.
Yeah.
Any other questions online? Here.
Okay, maybe I have a naive question.
Yeah.
What's the impact of the surface roughness on the wind energy production? You know, you can, when you select the wind from locations, there are some locations are, higher roughness, right? Some are not. How does that affect it?
So basically, we need a low surface roughness is better actually. So because if you have a higher surface roughness, sometimes it actually makes the wake recovery more complex actually to do the analysis. So before you build a wind farm, you need to do some kind of calculation. So if you have a smoother surface, you can do these calculations, or you can actually predict how much energy we can generate over 20 years or 30 years. But if you have complex geographical surface, it's kind of analysis become more complex because you can't. So the velocity profile itself is become very unpredictable for rougher surface. Yeah, to answer your question, smoother surface helps better than the rougher surface.
Okay, I see.
Yeah.
Any other questions? Did you use DNS? Do you think DNS will be useful this time? No, you can't actually because one term, yeah, I mean, it's a huge domain. Like if you see the domain size, this is the smallest domain size I used actually.
Okay.
So for like this case, like for example, this case is it's like 3 kilometer, 2 kilometer, and 1 kilometer. This is the like the smallest domain you can use for any LES or wind farm simulation, so wind turbine simulation. And I mean, it's impossible to
I know.
use PNS.
Because I saw the name here, DNS.
It's not Kolmogorov scale. It's just no turbulence model. So
Okay.
no trans.
I mean, yeah, people use RANs actually. Yeah, so they actually have coupled RANs and LES for the, especially for the what is it called? The surface of the turbine. They use RANs and also that the watt.
Yeah.
So yeah. So
basically, any CFD code has a DNS capability. Okay.
That's some books there.
Okay, so no more questions, then let's thank the speaker again. Thank you very much.